single place though, right? At one particular place, right here, let's call this again A, I'm not continuous. So at x equals A, not continuous. Why though? What do I have there? A hole. Why? Hole. We have a hole. And because we have a hole, I had to pick up my pencil and go to the other side and draw, right? So if you ever have a break in your graph or a jump like this, you're not going to be continuous wherever that jump's taking place. It's not continuous there. If you ever have a hole in your graph, it's not continuous. Would it make any difference in terms of being continuous if I actually define this to be like a point down here? Still not continuous, right? Because I'd have to still pick up my pencil to draw this. Questions?
Would you ever play around with, like, say, the tangent is continuous, but not on intervals of whatever the asymptotes are? I mean, would you ever be asked to mess with that? Or
Yeah, it's exactly what I'm about to do. Yeah, so what about a function that does this? Let's say the function goes like this. And over here, let's say it does this. And I tell you that I have a vertical asymptote. Let's call this A again, right? Do you agree that on this picture, I'm continuous everywhere except at A again? Like over to the left, this is all nice and connected. Draw it without picking up my pencil. Over here to the right, draw it without picking up my pencil. But at A, I have a problem. I have to pick up my pencil to get from one side of the asymptote to the other. So here, at x equals A, not continuous. I'm just going to say not CONT. Why? Vertical asymptote. I'm abbreviating vertical asymptote. For the first time, I'll tell you what it is. Vertical. You remember this from college algebra, right? Asymptote. It's a weird word. Vertical asymptote. So it's not continuous at the A because we have a vertical asymptote, all right? All right, so these are kind of like the different scenarios that would cause you to not be continuous. Now, anytime a function is not continuous at a point, we say it is discontinuous at A. So you would say this is discontinuous at A, this is discontinuous at A, this is discontinuous at A. That's the terminology. All right, you ready for the precise definition of continuity? Because right now this is just to get you thinking about what it is. You ready for me to put the precise definition? Well, ready or not. I always ask and then it doesn't matter. I'm going to do it anyway, right? But I like to ask first. Seems polite. Okay. A function f is said to be continuous at x equals A if, okay, if the following condition is met. The limit as x approaches A of that function equals the function's value at A. Okay, so that is the precise definition of continuity. I'll put it up here. This is what we call continuity at a point. Okay? If a function is going to be continuous at a point, then I need this to be true. So don't get all freaked out when you see this. We've talked about limits, right? So just look at the left side of this. When we talk about limits, if I don't do a plus or minus here, it means from which side? Both. Okay, so this is saying that in order to be continuous at some value A, the limit from both the left and the right of this function, right? This is from left and right limit. So imagine you're looking at the function, you're coming in from both sides, right? That limit has to be equal to what? the value of the function there. Value of f at a. Okay, let me go back over here and let's look at this right here. Why is it discontinuous here? Why? What is being broken in that definition? What is being broken here? The limit from each side doesn't even exist, does it? The limit from both sides is not the same. You have to have that for continuity. So just the fact that there's a jump means that the left side of this, right, the left side of this would be does not exist. Okay, what about this one? This one, the limit does exist, doesn't it? If I come in from both sides, it's headed to the same place, right? So the left side is good, right? That limit does exist. But what? Is it equal to the value of the function at that point? No, it's not. So where this limit is headed is not equal to the value of the function there. The only way that this would be true is if I did what with this point? Filled that hole with that point. But if I filled the hole with the point, then we'd no longer have to pick up our pencil, and they would be continuous, right? So what this is telling us, the definition of continuity says, look, if you go to the point, wherever it is on the graph, I'm just going to pick an arbitrary point. Let's say I go to this point right here. Am I continuous there? Yes, because I'm going to call it A again, even though I had to call that A. Why am I continuous at A? Well, because the limit from both sides is headed to the same place, and it's headed to the actual value of the function there. That's it. That's the definition of continuity. All right. Now, that's continuity at a point. What if I want to talk about continuity on an interval? Well, then it just means that you need to be continuous at every point in the interval. Right? So at every single point, you have that holding true. That would be continuity on an interval. So let me bring up my notes just so I don't have to write all this on the board. So this is it. Function said to be continuous at x equals a if this limit is true. That's what I have up on the board here. Okay, this is me just explaining what it means. And then here's graphical, right? Is this function continuous at 2? Yes or no? No, right? Why? Yeah, the whole. Does the limit exist? Yes, so the limit does exist, right? But is it equal to the function's value there? No. So that's why that one's not continuous. How about this one? Still not continuous, right? Does the limit exist? Yes. Is it equal to the function's value there? No. At 2? Yes, 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 right? Everything is good here. The limit exists, it's equal to the function's value there, and there it's continuous. All right, basic idea we can draw without picking up our pencil. Okay, if a function is not continuous at a point, we say it is discontinuous. I already said that. There are 3 types of discontinuities. A jump discontinuity, an infinite discontinuity, and a removable one. Those are the 3, and I have examples here. There's a jump. There's an infinite. This would be a vertical asymptote or something like that. And then a removable is something like this. We call this one removable. It's a weird name. We call that a removable discontinuity because it's an easy thing to fix. I could remove the fact that it's continuous by just simply filling in that hole. If I could just fill in that hole, everything would be great, wouldn't it? Notice on the previous 2, you can't do any easy fixes. Like you can't fix this. You can't connect these 2 together. If you do, you're changing the entire graph. Like it's going to make a dramatic impact on the graph. Same with this one. If you try and pull these together, you're no longer looking at the same thing anymore. Whereas opposed to this, just fill in the hole. It has no impact on anything else, and it fixes it. All right. There's something called left continuous and right continuous. We need to know what they are, so I'm going to show you a picture here. I'll put this on the board as well. The graph that you're looking at there is left continuous at A. So I want you to look at that. Is it continuous at A? Is it continuous at A? No, because there's a jump, right? But the way I drew it, solid dot, open hole, here's A. All right, so this is not continuous at A. But it is what we call left continuous at A. Left continuous. When we say left continuous, what we mean is go to A and just look at it from the left side. Okay? Am I approaching? I have a limit, right? It's headed to something, and is it filled in to be the function's value there? Yes, right? So it is left continuous. It is not right continuous, though, because from the right, it's headed somewhere, right? But that's not what it's defined to be at that point. So it's not right continuous, but it is left continuous. So left continuous and right continuous are weaker conditions than being continuous. To be continuous, you got to be both sides go in the same place, fill in the hole. Left and right only requires that from one side or the other. There's right continuous on the board over there, right? Do y'all agree that's right continuous at 2? All right. Continuity on an interval. A function f is said to be continuous on an interval if it is continuous at every point in the interval. And at the left end point, it only needs to be right continuous, and at the right end point, it only needs to be left continuous. What am I talking about? Okay, look at that. Look at that graph. That function is on a closed interval. It's defined on a closed interval. I have it starting at a point and ending at a point. And the question is that function continuous on that interval 1, 3? So I have this going like this. I'm saying this starts at 1, this stops at 3. And the question is this continuous everywhere in this interval between 1 and 3? The answer is yes. Because if you go any place here, right, we definitely have continuity at all these points, don't we? Mm-hmm. I mean, like really the strong continuity from both sides, fill in the hole, right? But when you get to the right endpoint and you go here, right, you can't talk about continuity like that anymore because you can't come in from the right side, can you? So when you get to the right endpoint, you only need left continuity. And then when you get to left endpoint, you only need right continuity. Yes?
If you change those brackets to parentheses and then you make those holes open,
great question.
say that's continuous?
Great question. I'm going to answer that. So this right here would be continuous on the entire interval 1, 3, right? That's what that would be. Continuous on the entire interval. You're asking, what if we change that to an open hole, do that, right? 1 to 3. Then this thing is defined on 1, 3, right? Not on the brackets. This you could say is continuous on 1, 3 without the brackets. But you can't put brackets on it, right? This would not be continuous at 1. It would not be right continuous at 1. And it definitely isn't left continuous because you can't look from the left. But see, no continuity at all at 1. Here, at 1, we are right continuous. I think that answers your question. We good? All right, let's keep going. Some theorems. I'm actually going to use this theorem later. We're going to read it and then just pack it up. We'll use it later. If you give me 2 continuous functions, right? So let's say I give you a continuous function. I think everyone here would agree that f of x equals 2x. That's a line, isn't it? That would be continuous everywhere. Draw a line? Yeah? Okay. What if I give you a different function, g of x? Let's go with x squared. That's a parabola, right? That's continuous everywhere as well? If you think about drawing it without you picking up a pencil. These are both continuous functions. This theorem says if we have 2 continuous functions, if you add these 2 functions together, create a new function by adding them or subtracting them, that new function will still be continuous. You never lose continuity if you start from 2 continuous functions and add or subtract them. All right? So if I created a new function, let's say I created a function, I'll call it h of x, and let's say it's I'll just add them, or I'll subtract them. If I draw this function, 2x minus x squared, that's still continuous. Guaranteed. Okay, theorem guarantees that. Also, if the number 2 says, if I take either of these and multiply them by a number, I'll still be continuous. So if I take this function 2x multiplied by 5, make it 10x, it's still continuous. Okay, so scaling it doesn't change continuity. Number 3 says we can multiply them, and we still have continuity. So if I multiply these 2 functions together, you still are going to have a continuous function. Fourth one says if I divide them, I still have continuity as well, as long as the bottom one is not 0. Wherever the bottom one is 0, you lose continuity. So I'll show you that. If I take, this isn't a very good one. Let me change this. 2x plus 1 is a line, yes? Okay, if I take 2x plus 1 over x squared, here's what I can tell you. This is a continuous function everywhere except where the bottom is 0. So at 0, at x equals 0, this would not be continuous, but everywhere else it is. All right? All right, finally we get to the most important part for us in terms of what we're going to take away from this, and that is what functions are continuous. What functions are, which functions aren't. And what I'm here to tell you is good news, is everything you've studied your whole life, college algebra, pre-cal, everything you've ever looked at is a continuous function on the implied domain of the functions. So like think about a polynomial. Remember polynomials in college algebra? They look like this, right? Like you were taught in college algebra, this thing called the leading coefficient test where you could figure out if both ends go up or down or, does that, you look like at the power and then you look at the leading coefficient, if it's positive, negative, odd, even, right? Yeah. That thing? Yeah. But they look like roller coasters. Yeah. All polynomials are continuous everywhere. All rational functions were those other ones in college algebra that you hated, where you would have all like vertical asymptotes, horizontal asymptotes, slant asymptotes. Remember all that? No? These are polynomials, continuous everywhere. Rational functions, things like this. Maybe it went like that, and then maybe it flattened out to a horizontal asymptote here. Maybe it did something like this. Maybe it had a vertical and then did, I don't know, something like that. I'm just making up a rational function here. Remember things that look like that in college algebra? These are all continuous except where your asymptotes are. So if you're to the left of this asymptote, that's nice and continuous. Between these two, nice and continuous. To the right, nice and continuous. You only have problems at the domain issues. Same with the trig functions. Sine and cosine, think about those. Continuous, right? Sine and cosine. Tangent, though, has some issues. We graphed tangent earlier. It's got asymptotes. Everywhere you don't have an asymptote, it is continuous. All exponential and logarithmic functions are all continuous functions on their domains. So I just gave some examples there. There's a polynomial. Here's a rational. Here's a trig. Here's an exponential. There's a logarithmic. Yeah. Last thing here. You know how I said if you add, subtract, multiply, divide, you still maintain continuity? It also works with composition. So if you do f of g of x or g of f of x, you maintain continuity that way as well. All right. How are we doing on time? 20 minutes? You all right? Okay, we've gotten to a very nice theorem called the intermediate value theorem, IVT. And I don't want you to read the theorem yet, just I want you to think about this visually. So IVT, intermediate value theorem. Let's say I tell you this. I'm going to have a function here. I'm going to draw it in a moment. I'm going to start this function at A, and I'm going to end this function at B. So it's going to be on a closed interval. I tell you that at A, I get some point here. Let's call this point, whatever it is, it's f of A. Okay, so whatever I get when I plug A into the function, that's how tall it is. That's that point, yeah? And then at B, I plug in, I tell you you're up here. F of B. And just for kind of giving you something to mess with, let's just say that this is, just as an example, let's say that that's 1, and let's say that that's 10 up there. So this point is 1 unit high, and that one's 10 units high. My question to you is this. Do you think that there's some value in here between a and b? Is there some number I can plug in to the function and ever get the number 7? Do you think that there's a dot somewhere in here? Can you also imagine a line that goes through here? Do you think that my graph ever hits that line? If it's continuous, it does, right? If it's continuous, it does. Right? It has to. I can't tell you exactly where it is, but if it's continuous, I've got to be able to connect those two dots together without picking up my pencil, which means I'm going to have to pass through that blue line at some point, right? So I'm going to call this right here, what do they call it here? N. Let's call this value here capital N, all right? If this function is continuous, if f is continuous on that interval AB, okay, so if I'm guaranteed between here and here I can't pick up my pencil, then somewhere in here, right, there's got to be somewhere that gets mapped to that and spits out the n, right? Somewhere. I don't know where, but it's got to exist. And I'm going to call this value C. So let me now read through that. Suppose f is a continuous function on a closed interval AB. So do y'all see this function f? It is a continuous function on a closed interval A to B, where f of A and f of B are not the same. So you have a different height on these points. These 2 points have different values. It says let n be any number you want between f of B and f of A. So you pick me any n you want. I don't care what it is. Just give me some value between 1 and 10, whatever you want. 7, 6, whatever. Okay? Let n be that number. Then the last thing says there exists a number C such that when you plug C into the function, it'll equal that. That's what the intermediate value theorem says. That's all it says. Does it seem reasonable? Now, believe it or not, this is a very powerful result. All right? You ready to see how it's powerful? See, I asked. It doesn't matter. I'm going to do it. Okay. Show cosine x equals x has at least one solution on the interval 0, 1. Okay, this seems like I'm coming out of nowhere with this at this point, right? Like, what in the world? We're talking about, continuity today and limits and this intermediate value theorem, and that all kind of is connected, but now I'm asking you to show me that that equation has a solution, right? I want you to show me that this has a solution somewhere between 0 and 1. So there's a number you can plug in here, somewhere between 0 and 1, that would solve this equation. Notice I'm not asking you for the solution. I'm only asking for you to prove to me that there is a solution somewhere between 0 and 1. So I'm going to start this off by going to Wolfram alpha. And I'm going to type into this, bless you, cosine x equals x. And it's going to spit out an answer. See the answer here? 0.739085. X is approximately 0.739085. Okay? Now we're cheating, right? We just used a computer to solve that problem. We know, so this just verifies there is an answer between 0 and 1, right? I'm not asking you to go find that answer. I'm trying to see if you can prove to me that there is an answer in here. All right? Here's how I'm going to do it. Oh, by the way, you cannot solve this by hand. Nobody in this class can solve that equation. Not even me. All right? If you take cosine x equals x and go solve for x, it's impossible to get x by itself. The only way you get x by itself is if it refers to itself. So here you can say, oh, it's solved for x, but that means in order to know x, I need to know x, right? So you can't tell me it's solved for x. What else could you do? Maybe you get, try and be clever. You're like, oh, well, I learned in pre-cal these inverse trig functions. So I'll do the inverse trig on that side, and then I'll do inverse trig on this side. And I know that these two kill each other off, you get x. Yeah, I freed it from the cosine, but then over here it's still trapped. Now it's trapped in the inverse cosine function. So there's just no way to get x by itself. All right? So there's no algebraic hand method that we can solve this equation. There's a lot of equations like that. So what I'm going to do is this. All right? I'm going to use the intermediate value theorem. Okay? I'm going to use this. Watch the way I do it. First, let me start with this. Let f of x, I'm going to define a function right now. I'm going to define a function. I'm going to let it be cosine x minus x. All this function is, what I want you to see, all it is what I would get if I moved that x to the other side of the equation, right? So imagine moving the x to the other side of the equation and just ignoring the equal sign. That would be what I would have, right? Now, I'm going to try to find the x-intercepts of this function. How do you find the x-intercepts of any function?
Plug in 0 for y.
Plug in 0 for y, or set the function equal to 0, right? So cosine x minus x, set it equal to 0, right? But that's what we're trying to solve, isn't it? So back up. I wanted to solve this equation, moved everything to the left side, and called that a function. And now I'm looking at this problem as trying to find the x-intercepts of that function, right? Solving that equation is equivalent to finding the x-intercepts of that function. Yeah? Okay, my question to you, is f continuous? Yay or nay? Is this function f continuous?
Yes.
Why?
Because you're subtracting two continuous functions.
Exactly. Cosine by itself is continuous. Why? I told you all trig functions are continuous, right? Okay, the function x by itself is a line. That's continuous, right? Or you could say trig and polynomial. Subtracting two continuous functions is a continuous function. So this is continuous, right? On its implied domain. So everywhere, tangent would be continuous as long as you were talking about places where it didn't have vertical asymptotes. So this is continuous everywhere, isn't it? Everywhere, because there's no problems with domain on these two functions. So if it's continuous, does the intermediate value theorem apply? Does this theorem apply?
Yes.
Yeah, because that intermediate value theorem talks about what happens if you have a continuous function, right? This is a continuous function, and now I want to look at on the interval 0, 1. Watch this. This is the part that's the big. This is like a whoa, but it's almost so subtle it's not a whoa. All right. So watch. What I'm going to do is this. I'm going to plug 0 into this function. I'm going to plug the left endpoint into this function. So what happens if you plug 0 in here? Cosine of 0 is 1 minus 0. So you get 1. Okay. And then I'm going to plug the right endpoint, 1, into it. So now I have what? Plug in 1. Well, you might need a calculator for this. Cosine of 1, you'd have to be in radian mode on your calculator. And then minus 1. So I'm going to need someone to do that. Is it negative point? Are you in radian mode? Yes? Should be a negative number. You sure? Can I see? Oh, no, you never subtracted 1. Sorry. Wait, what did I put? Yeah, because we're plugging it in right here, right? So you're doing cosine of 1 and then take away 1. Negative 0.45. 9, whatever. Okay. All right? What the heck? What am I doing? Am I confusing you at this point or no? Do y'all see where I'm headed with this? I'll leave that picture up. Think about graphically what we just did. This function f looks like something, right? It's continuous. And I just said at 0, what was the value of the function at 0? 1. And then I went out to 1, and what was the value of the function? negative, right? Something, negative something. So now I have a point down here, don't I? And it's continuous, which means that this point and this point have to be connected. It's like, you know, I can't pick up my pencil, which means I have to pass through the x-axis, right? Isn't that what we were looking for, though? We were looking for where this function had an x-intercept, right? Find the x-intercept of this function. So I was trying to prove to you that there is going to be an x-intercept. And since this has to be connected with a continuous function, it's going to have to pass somewhere. I don't know where, but I'm guaranteed. I'm guaranteed if I go from a positive number, if I go from positive to a negative number, right? If I go from a positive to a negative, then I have to pass through what? 0, right? As long as you're continuous. You're going to have to go at some point through 0. And that's enough to prove that there's a solution. It's kind of weird now. So if I asked you to solve an equation on an interval, what you do is you move everything to one side, call that your function. You would evaluate it at both endpoints and show that there's a change in sign. If there's a change in sign, you pass through 0, you have an x-intercept, which is the solution to the equation. Believe it or not, that's what this calculator, Wolfram Alpha, that's exactly what it did. But how did it get the answer, right? How did it actually get an answer? Computer science majors, you know? Any computer science? Only one? Only one computer science. This summer I had none in my college algebra. So let's see if y'all can all follow this. Imagine you're a computer, all right? And somebody types in cosine x equals x and wants you to solve this, right? The computer's going to look at this as this. It's going to move everything to one side, and it's trying to figure out where it's 0, right? So what it does first is it just takes a random guess at 2 different points. And it just plugs 2 different values into that. Now, just for the sake of demonstration, I'm going to act like it picked 0 and 1. Okay, so it picks 0. We know that when we plug in 0, we got a positive number. And then at 1, we got a negative, right? So the computer now knows there's a solution somewhere between here. So what it does is it cuts this interval in half. And now what it does is it plugs 1/2 into that function. All right? Now if you do it, if you plug 1/2 in on your calculator, you're going to get a positive number again. So now your computer says, all right, I knew I went from positive to negative between 0 and 1. And now between 0 and 1/2, I stay positive. But from 1/2 to 1, I go from positive to negative, which means the answer must be somewhere in here, right? So it cuts that in half, which would be 3/4, 0.75. Now, if you plug 0.75 into your calculator and plug it into that function, you will get a negative number. I'm exaggerating here. It'll be negative. So now the computer says, okay, between 1/2 and 0.75, it changes signs. Between 0.75 and 1, it doesn't. So the answer has to be in here. And then it cuts it in half again, and then checks both sides. And it keeps doing that. Do you see what it's doing here?